In a previous video, I solved Cauchy's additive functional equation for all continuous functions using the ZQR method. In this case, the functions that solve the equation are the functions of the form c times x, with c an arbitrary constant. It was also commented in the previous video that the continuity of the function can be replaced by other weaker conditions, but always the same solutions emerge. For this reason, it was thought that Cauchy's additive solution is always solved by the linear functions c times x, even when no additional condition is added. However, in 1905, the German mathematician George Hamel surprised mathematicians by proving that this general expectation was not correct. In this video, I will show to you Hamel's solution for Cauchy's additive functional equation without requiring the continuity of the functions. To understand the solution, you must first understand the concept of the Hamel basis for the real numbers. In one of my algebra videos, I commented that given a field f and a subfield k of f, then f can be considered as an algebra with scalars in k. In the present case, f is the field of the real numbers, and k is the subfield of the rational numbers. Hence, the real numbers can be considered as a vector space with the scalars being the rational numbers. A vector space is enough. An algebra has even more structure, but the additional structure is not important. If the set of real numbers is a vector space, there's a set of real numbers which forms a basis, and every real number can be expressed as a linear combination of the elements of the basis with the coefficients of the linear combination being rational numbers. Let me be more formal. A subset H of the real numbers is called a Hamel basis if for every real number x there exists a finite number of elements h1, h2, up to hn of the basis h such that x is written in a unique way as a linear combination of these elements with rational coefficients. The expression of x in terms of the basis elements is known as the Hamel decomposition of the real number x. The definition of a Hamel basis does not guarantee its existence. Hamel's contribution was to prove that at least one Hamel basis exists. To do so, Hamel used the axiom of choice, which states, given a collection of non-empty sets C, there is a function f such that it maps each set x of the collection to an element that belongs to the set x. Said informally, the axiom of choice guarantees that given any collection of sets, we can always form a set which contains a single element from each set of the collection C. The axiom of choice appears quite natural. However, it leads to certain results that some mathematicians consider paradoxical, and hence, they have argued that it should be dropped from mathematics. Despite this objection, most mathematicians accept it. Once the axiom of choice is accepted, a Hamel basis exists. For topological reasons, the Hamel basis must necessarily be uncountable. Unfortunately, there is no known explicit example of a Hamel basis. We are now ready to present Hamel's solution to Cauchy's additive functional equation. We will split the solution in two parts. The first part deals with the direct statement, the necessary condition. That is, the condition the function satisfies if it is a solution of Cauchy's equation. The second part deals with the inverse statement, the sufficient condition. That is, the condition the function must satisfy to become a solution of Cauchy's equation. Let's state the direct statement. If the function f is a solution of Cauchy's additive equation, then it maps the real number x with a Hamel decomposition q1 times h1 plus q2 times h2, and so on, to the linear combination of the images of the basis elements with the same coefficients. To prove it, recall that any solution of Cauchy's equation satisfies the following equation. For any set of n real numbers, this equation can be proved inductively from the given equation. Then, we set each x to be a rational number q times a real number h. Also recall that for any rational number q, we had shown that f of q is q times f of 1. You can rerun the argument to see that the statement is true not only for q times 1, but also for q times any number y. Applying this result in the right-hand side of equation 1, we find that the image of x is a linear combination of the images of the basis elements that enter its Hamel decomposition. Also, the coefficients are exactly the coefficients that appear in the Hamel decomposition of x. Now, Let's look at the inverse statement. If a function f is constructed such that arbitrary real values are assigned to the elements of the Hamel basis, and any real number x with a Hamel decomposition q1 times h1 plus q2 times h2, and so on, is mapped to the linear combination of the images of the basis elements with the same coefficients, then the function is a solution of Cauchy's equation. To prove it, consider two real numbers x and y with their Hamel decompositions. In general, the two sets of the Hamel elements which appear in the two decompositions are distinct. However, their number is finite. We relabel the union of the two sets, and we re-express x, y, and their sum in terms of the relabeled elements, and using zero coefficients for those elements that do not appear in the decompositions. Then, according to the hypothesis, the images of x, y, and x plus y are the corresponding linear superpositions of the images of the Hamel elements. By a simple comparison, we immediately see that f satisfies the Cauchy equation. Therefore, we have shown that the most general solution f to the additive Cauchy equation is found by following the next three steps. 1. Introducing a Hamel basis h in the set of real numbers. 2. Assigning arbitrary values for f at the elements of the Hamel basis. 3. Setting the image of a real number x using its Hamel decomposition and the following rule. Given what we know for the continuous solutions of Cauchy's additive equation, we can state the following theorem immediately. A solution of the Cauchy additive equation is continuous if and only if there exists a real number c such that each element h of the Hamel basis is mapped to c times h. And with this comment, I have concluded this video on the most general solution of the additive Cauchy equation. I hope you liked it. If you did, please subscribe to my channel to help the creation of more videos. Thanks a lot for your support.